Welcome back. Today we're going to talk about constructing a confidence interval for means. We've talked about constructing a sample interval for proportions, but let's talk about constructing a confidence interval for means. Well, guess what? We've got conditions. Just like we had conditions when we were doing proportion, we wanted it to, be a random sample. We wanted to meet the 10% condition. We wanted it to be normal. We want the same things for this. So one of our conditions is it needs to be a random sample. And the reason why it needs to be a random sample is so that it's representative of the population. Number two, it needs to meet the 10% condition. And therefore, it won't have its own mean. Number three, it needs to be normal. So what does that mean for us in this scenario? Well, the population could be approximately normal. The number greater than 30, and we could use the central limit theorem. Yeah, so number greater than 30, it's got that normality to it. And the sample shows no strong skew or outliers. So this is kind of like an either or. So we've got this, the population could be approximately normal, then we go with it, right? Sample less than 30. Or if the number is greater than 30, we can use the central limit theorem to say that the sampling distribution of sample means is normal. Let's say we don't have an approximately normal data set, and we have a number less than 30. Well, that's when you would look at your graph and see if the sample shows skewness or outliers. So what are we doing with this? Well, this is actually going to look super familiar to you. And what we're going to be doing is going to be called a one sample Z interval for population mean. And our formula looks like this. X bar, sample mean, plus or minus T star, we'll talk about that in a minute, and Sx over the square root of n. Well, if you think about this for a minute, what did we do last time? Last time we talked about how we've got our sample proportion, right, p hat, is equal, or sample proportion, or point estimate, plus or minus Z star times, and then it was our standard error, which was our standard deviation. Well, think about it like this. This right here is like our standard deviation, yeah? And this is our sample mean. And so we just need to know what T star is. Well, T star, we have a chart for that. T star comes from table B. And what we're going to do is we use it for means. Okay, if we're doing sample means, confidence interval for the means, and we're using a concept called degrees of freedom. It's one of the charts. I'm going to show you the chart in a minute. Degrees of freedom is equal to n minus 1, and so we're going to use table B, and we're going to find the confidence interval. And our degrees of freedom. Check it out. So one of the things, well, I'll just show you. Okay, here we go. So here's our table. Let me zoom in on it a little bit. So check it out. What we have here is too much zoom. Up here we have our confidence intervals. See there? So 80%, 90%, 95, 98, 99, 99.8. Very common. Over here we have degrees of freedom. So let's say, for example, we have a sample size of 28. So our degrees of freedom would be 27. And we want a 95% confidence interval. So it goes 27, 95% confidence interval. So 2.052 would be our critical value there, our T star in this case, because we're using sample means. Common areas where students get confused, do they use T star or Z star? Well, if you're using sample means, you do T star. If you're using proportions, you use Z star. And so that's kind of the basic gist, how we use this concept here. So what are the potential downfalls? Check this out. Well, if you get down here, you see it jumps from 30 to 40 to 50 to 60 to 80, skips 90, 100, and then infinity. So what are we going to do? Well, we are always going to round down if it isn't on table B. Round T star down if not on table B. So for example, let's say I get 90. I'm going to round that down to 80. Okay, so I'm going to round that down to 80. So that's kind of how this works. Same principle as yesterday. We're constructing this confidence interval using a critical value. Okay, actually I'm going to label that. So this is the T star is a critical value. So you can tie that together with what we talked about last time, value, right? Because Z star was a critical value. So let's do an example. Use table B to find the critical value T star that you would use for a confidence interval of a population mean M in each of the following settings. If possible, check your answer with technology. So first one, a 96% confidence interval based on a random sample of 22 observations. So our T star is going to be based on our degrees of freedom. I'll just write it out, degrees of freedom. And it's going to be equal to n minus 1, so therefore it's going to be 21. And so we'll go over to our chart. Let's go to line 21 here, and we wanted a 95% confidence interval, 96% confidence interval. So what's the problem here? Well, when we go to our line here, we see that we don't have a 96% confidence interval. So check it out. I want you to look at this. We're actually calculating the right tail probability, right? So what's the right tail based upon? The right tail is based upon, again, we've got that confidence interval in the middle, so half of what's left. And so for me, there's a new function that we need to use. We can use inverse t on our calculator. Inverse t, so it's right by inverse norm. So we're going to do inverse t of, we're going to do 1 minus the percent over 2, comma, and then we're going to put in our degrees of freedom. Okay, so in this case, we're going to use the function inverse t. Now, we went to the table first. It wasn't there. There's no 96% confidence interval, but because it's based on a tail, middle portion, right? So the concept is like this. So if I have a 96% confidence interval, then I've got 2% over here. I've got 2% over here to make up the 100%. So in my case, I'd have inverse t, 0.02, comma 21. And when I do that, I get 2.189. That's my critical value. So if I was given standard deviation, if I was given the number in the sample size, I have 22. But I could figure out exactly what was my confidence interval, what it actually was based on that critical value. All right, next one. 99% confidence interval. I know that one's on the table B. From an interval from an SRS of 71 observations. So random observations, here we go. 99% confidence interval, so I'm in this column here, and I'm going down to, well, what am I going down to? This would mean that degrees of freedom is equal to 70, which is great. That one's going to be on my chart, I think. And, oh boy, it's not. So what am I going to have to do? So I'm going to have to use 60 for my chart. So let's see how this differs. We're going to do it two ways. We're going to do it from the chart. We're going to do it from inverse t. So here's 60. My 99% confidence interval is my second to last column. So I've got 2.660. So here we go. Table B. We have degrees of freedom equals 70, but in the chart there's got to be 60. So my T star was equal to 2.660. Let's think about if we did inverse t here. If I did inverse t, I've got a 99% confidence interval, so I have 0.05 here, right? 0.05, because I've got 1% left. And then I'm actually going to put in my degrees of freedom here. Well, when I do that, I end up with 2.648. Look at the difference there. Okay, so your calculator is going to give you a more specific answer, but again, you need to make sure you label this so you've got your inverse t going. Don't just put 0.005 to 0.70. So what's the answer that I would accept? So did you find use table B? So it says use table B, so they would accept 2.660 here. Okay, let's do an actual problem. Judy is interested in the reading level of a medical student or a medical journal. She records the length of a random sample of words. The histogram displays the distribution of word length in her sample. Determine her conditions for constructing a confidence interval for a mean that have been met in this context. So let's go through the process. 1. Is it random? Yes, it is. We have evidence here. Random sample. It says random sample. Does it meet the 10% condition? So a medical journal is 10% condition met. Let's see. Is 100 less than 1/10 of all the words in journal? Yes. They're not going to catch us on that technicality. And number 3, is it normal? Let's see. Records the length of the sample. Oh, 100 words. So 100 is greater than 30. So by CLT, it's normal. Done. That's it. Okay. So determine if the conditions for constructing a confidence interval for the mean have been met in this context. Yes, they have, because we have those 3 conditions met. All right. So that's the first part. That's what we're doing. So it should be vaguely the same as what we've done, right? So we've got the same process. We check the conditions and we use a different formula, but it's based on the same principle. So what about the 4 steps? Let's take a look. In this case, the 4 steps would be this. We're going to state, right? We're going to state what the true mean is. Okay? We're going to plan. And when we plan, what we need to do is we're planning to do a certain process. What's that process called? It's called the one sample t interval for the mean. Now that might seem, well, we just said z. Well, we use t in this case because we're using a different table to calculate it, but it's really the same thing. Okay, let's see. So what is in our plan? Well, we need to meet the normal condition. So either the population is normal. This is what we were talking about, right? So if it says the population is normal, then the sample would be normal. Or we have a number greater than 30 in our sample, which would allow us to use the central limit theorem. Or we could, if we have less than 30 and no normal distribution, we could say that its sample shows no strong skew or outliers. And so what are we going to do? We are going to do, and I'm running out of space for my 4 steps, right? So we're going to do this, x bar plus or minus. And we're going to do t star times, and this right here. T star times the standard deviation over n. That's going to be our sample error, if it were, as it were, right, for our margin of error from our last one. But the sample is the standard deviation over n. And then we're going to conclude. Okay. So our margin of error that's our t star times this standard deviation over n. If we can't know, we're going to use z star in its place, right? So if we don't know what the sample size is, for example, we haven't run the study yet. If we don't know if we don't know our standard deviation for whatever reason, if we can't find t star, we're going to use z star in place. T star is unknown. So here we go. Administrators at your school want to estimate how much time students spend on homework on average during a typical week. They want to estimate this mean at a 90% confidence interval with a margin of error of at least 30 minutes. A pilot study, at most 30 minutes, sorry. A pilot study indicated that the standard deviation of time spent on homework per week is about 154 minutes. How many students need to be surveyed to meet the administrator's goal? So it states our margin of error is 30, and it's equal to, and what are we doing here? So how do we figure out our t star? We're just going to leave it for a second here. And then we're going to do 154, and we're going to divide by n. So we don't know the sample size, so that's what we're going to be trying to find. But what we're doing is we are going to use we're going to use z star instead because we have two unknowns. So we're going to use z star for 90%. So that's going to be 30 equals 1.645 times 154 over the square root of n. Well, when we do a little solving here, right? So we divide 30 by 1.645. So I've got my math here. The square root of n is equal to 1.645 times 154 over 30. And so then when we square that, we get n is equal to, well, actually we squared both sides, right? We get n is equal to 71.31, and we're going to round up, so that means that we need to survey 72 students. Okay, so let's work on this problem here. Biologists studying the healing of skin wounds measure the rate at which new cells close the cut made in the skin of an anesthetized newt. Here are the data from a random sample of 18 newts measured in micrometers per hour. So here we go. So what are we trying to figure out? Calculate and interpret the 95% confidence interval, the healing rate of U. So state, we want estimate the true mean for healing rate at 95% confidence. So plan. Do a one sample. T interval for U. Sorry, for mean. Is it random? Meets the first condition. Let's see. Random sample. Yes. So they said random sample right here. Is it meeting the 10% condition? Yes, because our 18 is less than 1/10 of all newts. Is it normal? Let's see. We're less than 30, and it doesn't say normal, but if we observe here, we have, and this is just a general here, you draw out a bar graph. So I obviously have the answer, and so I have an advantage here. But if you drew this out and you put them in intervals like this, right? So we go 10, 20, 30, and 40. We see no strong skew and no outliers, right? So we could say, yes, it's going to meet this condition. So we're going to do a point estimate. And we do our point estimate plus or minus our margin of error. We're going to have x bar plus or minus t star times our standard deviation over our square root of our population. And when we do this, we're going to end up with, and so what we get here when we do this, evaluating that t star value, is we end up getting 25.67. So that's going to be our point estimate, right? And then we're going to plus or minus. So where do we get this? We took the mean of these. You know, you take the mean of these, and you get that 25.67, and then you've got 2.110, and then 8.32 over square root of 18. And so when we're looking at this, you know, that gives us an interval of 21.53 to 29.81. Okay, so how do we do that? So we found our standard deviation, okay, from this list of values. We divided it by the square root of the number of values that we have. And we got that 2.110 given our t star from that 18. So how do we conclude? We are 95% confident that the true mean micrometers per hour falls in the interval from 21.53 to 29.81. Okay, so we're 95% confident that the true mean falls in that interval for healing of newts in micrometers. So that's how you do it. I think the part that I kind of breezed over a little bit was this part here, but all these calculations are old calculations, right? Finding a mean, and now we're using it as a point estimate. Finding this t star score using our degrees of freedom and our confidence interval, right? So we want to be 95% confident on that 20%, and then we want, or 95% confident on that 20 degrees of freedom, and then finding our standard deviation, which we've done in the past, dividing by the number, establishing that interval, and then interpreting it in context. That 95% confidence interval means we're 95% confident that the true mean falls in this interval. Okay, that's all there is to it, guys. So let me know if you have any questions, and we'll see you next time.